Let's record. All right, and I did a full revamp on the notes on the videos. So let me show you one last thing. This is the website. The 3-4 has just posted. So you see 3-4, 3-3 complete lectures. 3-2 is broken up into two pieces. If there's a date in the front and then it says class, that is a video that was taken during class for this class, for just this class. There's no one else's videos on here. So these are the exact lectures that we did, includes all the pauses, all the, work on this, and I walk away for a few minutes. And a playlist contains the, you have a link to a playlist. Both playlists contain all the lectures and all of the fill in the blank ones, where if it doesn't have a date and class in the first one, it was me doing a problem or doing an example because I said I'll do this after class and post it. And then at the end is all the way at the bottom there in order. You'll see the 3-1, 3-2, 3-3, 3-4 stuff. And 3-1 is what we did in class. That lecture is complete because I stuck around after class and finished it. So 3-1 is done, 3-2 is done, 3-3, and 3-4. All right, so let's dive into 3.2 and exponential functions. Before I explain exponential functions, the first thing I want to do is remind you of some rules for exponential functions. All right, and those are exponent rules. So if I have the same base and I'm multiplying, what I do is I get to take the exponents and add them. So m to the 5th times m cubed is m to the 5 plus 3, which is m to the 8. Nobody's shocked by that. Everybody remembers that. Here's the one that gets people. When I have a fractional power, what this means, so let me give you a generalized example here. If I have some number x raised to the 1 over n, that means I have the nth root of x. So the denominator determines which root I'm looking at. If it's a 2, it's a second root, which is a square root. If it's a 3, it's a cube root. If it's 4, it's a fourth root, so on and so forth. So 49 to the 1/2 power is the square root of 49. And the square root of 49 plus and minus 7. Okay, 3 to the -1. You have x raised to the -n. That means you really have 1 over x to the n. X is in the numerator. It's supposed to be in the denominator. That's what that negative sign tells me. Likewise, if you have x to the -n in the denominator, what you actually have is x to the n in the numerator. Okay. That property is used to make, there's lots of places it's used. One of them is to make equations not have so many fractions by just pulling this from the denominator up to the numerator and giving it a negative power. It just makes things look less complicated. So what is 3 to the -1? It's 1 over 3 to the 1st, which is 1/3. The reason I put the 1 there is to drive home the point. The negative goes away when this is moved to the correct location. The power stays. So if this was 3 to the -2, this would be 1 over 3 squared. Continuing, if I have a power raised to a power, I multiply. So if I have x to the m raised to the n, that is x to the m times n. Remember, if I'm multiplying the same bases, I add the powers. If I'm raising a power to a power, I multiply them. So -3a b to the 7th all cubed is I cube -3, I cube a, and I cube b to the 7th. -3 times -3 is +9. +9 times -3 is -27. A to the 3rd is a to the 3rd. B to the 7th raised to the 3rd is b to the 21st. You can do that all in one step. Again, this is me making notes for the class, so I will probably explain a little bit more than is necessary. 27 to the negative 2/3. So let's think about this. If I said it was, well, let me get this right first. First off, power is negative, right? So this is 27 to the negative 2/3. This is currently in the numerator. Why is it in the numerator? If there's no denominator, there's always that understood 1 there in the denominator. So 27 to the negative 2/3 is in the numerator. It's supposed to be in the denominator, which means I'm supposed to have 1 over 27 to the 2/3. Notice the sign the sign goes away. Don't like angled fractions. Raised to the 2/3. So the denominator of a fractional power tells me the index of the root. So that fact that it's 2/3, because that 3 is on the bottom, this is a cubed root. And then the numerator is the power that you raise the number 2. Some little Dr. Evil there, number 2. 27 squared. All right. If you're not sure about that, I want you to think about x to the 3rd. That's really x to the 3 over 1, right? So the 3 is just the power that you're raising the number or variable to. The denominator is the root. If you do that out, and I don't expect you to be able to take, well, you could, yeah, you should be able to do that. The cubed root of 27 squared, square 27, and then take the 3rd root. And I think, what do you end up with? Oh, you end up with 9. Because that's what the calculator says. Now, if I take 27 squared, I can rewrite 27 as 3 cubed. 3 cubed squared is 3 to the 6th, and then take the cube root, you end up with 3 squared, which is 9. But this, again, I wouldn't expect you to do that by hand. What am I doing? It's not 9. The 9 is where is in the denominator, but there we go. That makes way more sense. But yeah, I expect that to be done in the calculator. You can do it in the calculator with the fraction, with fractional power, or you can do it in the calculator if you've got a calculator that does cube root. You can also do it in Desmos. Next is the tougher one, but it's not because of the concept, it's because we're dealing with fractions. I have the same base and I'm multiplying, so that means a to the negative 3/4 times a to the 6th. Notice I didn't bring that a to the 3/4 down because I don't have to. It's not required. Instead, I'm just going to have the same base and powers. I'm going to add them, right? So negative 3/4 plus 6. I need a common denominator. 6 is currently 6 over 1. I need a denominator of 4. How do I get a denominator of 4? I multiply top and bottom by 4. And now I'm looking at a to the negative 3/4 plus 24 over 4. And that is negative 3 plus 24 is 21. That's a to the 21 over 4. That's fine the way it is. This is also the 4th root of a to the 21st, but I have a feeling that's where you're going to want to stop. Okay, but they both mean the same thing. All right, really just working on driving that point home. That denominator of a fractional power is the index of the root. Last 3, haven't seen this one yet. When you have division with the same base, it is subtraction of powers. M to the 7th divided by m to the 5th is m to the 7 minus 5, which is m squared. If you're wondering why or how that works, yeah, why or how that works, this is 7. So if I write this out, that's m to the 7th is 7 factors of m. M to the 5th is 5 factors of m. 1, all the m's, 3 m's, that's 4 of them, that's 5 of them. All those divide away, leaving me what? M times m, which is m squared. That's why it works. Now, let's flip it, and let me show you what happens. Forget the writing it out. M to the 4th divided by m to the 9th. Okay? Numerator has a smaller power than the denominator. That does not change how the math works. Okay? I'm dividing with the same base, so I subtract. The numerator's power goes first, the denominator's goes second, and I end up with what? 4 minus 9, which is -5. You typically don't leave answers with negative powers. So what does m to the -5 mean? It's 1 over m to the 5th. All right. If you're doing division and you end up with a negative power, it means that there were more factors of m in the denominator than the numerator. How many more? In this case, 5. So that means when I get done with the problem, there'll be 5 factors of m in the denominator. Next, 15 times y to the 0. Rule here, anything to the 0 power is 1. And then there's always the rule except 0 to the 0, which is undefined. So 15 times y to the 0 is 15 times y to the 0 is 1, because anything to the 0 power is 1. So I just get 15. And then lastly, power to the power, same idea. N to the 5th all raised to the a plus b is n to the 5 times a plus b. Distribute the 5. That's n to the 5a plus 5b. And you can stop there. You have consolidated. You have a single factor of n. Or if you want to take it another step, I have addition in the powers, which means this could be rewritten as multiplication with the same base. Right? I want you to be able to do this backwards and forwards. I want you to be able to do powers raised to powers. I want you to be able to take, when I have the same base multiplied, you add or subtract the power, or the same base divided, subtract, and then it goes the other direction. If you have one factor that has addition in the exponent, you know to break that. That can be broken up into multiplication. If you have one factor that has a fraction in the exponent, you can break it down into its root and its power. All right, so these are just the main rules from exponential functions. And then here is our definition. You're going to see it again at the top of the next page. Let b be a constant real number such that b is greater than 0 and b is not equal to 1. For any real number x, a function of the form f of x is equal to b to the x is called an exponential function of base b. So b is the base. I tried to stay consistent. Anytime there's a base that appears in this chapter, it's always represented by the letter b. Sometimes, and in the textbook, you will see it represented by a. Don't let that throw you. It's sometimes they're written as a to the x. Sometimes they're written as b to the x. Your notes, the old notes, actually have a's on the next page, but I've changed them all to b's in here. All right, so there are two rules. B has to remain positive. B is greater than 0, which means b is positive. And b is not equal to 1. Okay, now b has to be positive because we would lose if I had a negative number down here and I raised it to a power, the function wouldn't act like an exponential function. It wouldn't have the behavior that we're interested in. So b is positive, okay, and when I say notice the difference here. It's not 0 or positive. It's positive. B is not allowed to be 0, and b is not allowed to be 1 because if b is 1, so f of x is equal to b to the x. So what do you get 1 to the x. Pick a value of x and raise it. F at 3, that's 1 cubed, which is 1. F at -5, that's 1 over 1 to the 5th. Excuse me, yeah, 1 over, I did 2 steps in my head there, sorry, 1 raised to the -5. It will always be 1, exactly, which equals 1. So it's boring. So that's why it can't be 1. It's always positive because the base always has to be a positive number. And what's it look like? All right. There are examples here in the notes, but we've seen what happens when I try to draw a curve on my pad, so I'm not going to do that. I'm just going to go grab these two functions. F of x is equal to 2 to the x. Next one, f of x, g of x is 2 raised to, Desmos has made a small change in their, when you're doing exponents, you have to put a parenthesis first, or it's gonna assume that the next thing that you type in, so like if I type x, or sorry, if I do that and then do x and just keep typing, it jumped down automatically on me earlier today. So here are the three functions. What do they look like? Well, here is f of x, 2 to the x. What's happening? As x gets larger, what's happening to my function? It's growing, and this is what exponential growth looks like, right? It takes no time at all for the y values to shoot off to whatever, to the 2 to the 4th is 16, 2 to the 6th is 64, right? And then 2 to the 10th is 1,024. We've reached the point where we're starting to see exponential growth. What's happening is x goes more and more negative. Well, as x gets more and more negative, the power of x is negative, which means that 2 is not supposed to be in the numerator, it's supposed to be in the denominator. So what's going on? 2 to the -2 is 1 over 2 squared, which is 1/4. 2 to the -4 is 1 over 2 to the 4th, which is 1/16. The more negative I go, the closer, the larger the denominator gets, which means if I have a fraction and the denominator is getting larger and larger and the numerator is not moving, I'm running off toward 0. I'm never going to reach it because this will always be some non-zero value, but it's going to sit there. It's going to hug that horizontal axis. It's going to hug that x-axis all the way. Yeah. Now, if I manipulate, so just like our transformations that we dealt with before, we talked about I can change the inside, I can change the outside, and then I can put negative, and then negatives on the inside and outside change the behavior. So 2 to the x plus 3. So the inside, in terms of transitions, is the exponent. So by putting that plus 3 in there, what I've done is I've moved f of x to the left 3 units. Right? So if I come over here and look for values, so 0, 1 has now become -3, 1. Right? Everything got shifted left. What about when I put a negative in there? Well, now I have flipped across the y-axis. Let's continue and do something to the outside and just show you that that's the case. So plus 5, a plus 5 on the outside would move it up 5 units. Minus 3 would move my function down 3 units. So that's what our transformations told us. So all those rules still apply. So instead of graphing those out on there. I just wanted to show it to you that way. The other thing I need to introduce is the number E. And I know you're thinking, E is a letter. Why would you want to tell me E is a number? It is. It is, as this algebraic expression grows, 1 plus 1 over x to the x, as this continues to grow, as x gets larger and larger, you would think that if I keep raising something that's non-zero to a higher and higher power, it would grow forever. It turns out that's not the case. There are expressions that if you let x go as large as you want, the entire expression itself is not going to go past its limit. It's not going to go, there's going to be a number that it cannot quite reach, just like the exponential exponential function. As it goes off toward negative infinity, it never reaches zero. It keeps getting closer and closer, but it never reaches it. Same thing's happening here. So as x goes off to infinity, it turns out 1 plus 1 over x to the x keeps getting closer and closer to the number E. All right? All right, it'll never reach it, but that's the number. So this is where it comes from. And when you go on to calculus, the first thing you're going to learn in calculus is a limit. And what is a limit is just what is the behavior as x gets really, really close to the value that's under it. Well, right now this is x as x goes off to infinity. 1 plus 1 over x to the x, the limit of that is E. So as x continues to grow, whenever you see that x to the positive or negative infinity, you're really just looking at end behavior. What's happening as x gets larger and larger? So that's a limit. Okay, e to the x, here's a graph of it. Okay, e is just a number, so treat it that way. This is no different than if I had 5 to the x or negative 3 to the x or pi to the x. They're all numbers. All right. Now, here is again the same definition from the first or second page. B is greater than 0, B is not 1. Then I have an exponential function of base b. So I have to consider two properties. The first one, this graph is of f of x is e to the x. And what's going on here is that my base is greater than 1. Okay, my base is e. E is 2.7 whatever. So as x grows, my function grows, right? E to the second, e to the fourth, e to the eighth. That's continuing to grow, so that heads off to positive infinity. As x goes more and more negative, this becomes a fraction that keeps getting closer and closer to 0. Now, what happens if I change the base to be, instead of greater than 1, I'm going to change it to be less than 1, and I do need to make a tiny adjustment there. Not exactly, and the adjustment is done in the note in the lecture. I want to really point out that b is between 0 and 1 because b is not allowed to be 0, b is not allowed to be negative. So if I have a base that's between 0 and 1, what happens? Well, it flipped, right? It kind of looks like it sat up or laid down, just kind of flopped over, right? What did it actually do? It has transformed, or it's flipped across that y-axis. Because now as x goes off toward negative infinity, the function's going off to positive infinity. And as x goes off to positive infinity, my function is diving for 0. Why is that? Because as x gets larger and larger, x is 100,000, a million, 1 to a million is 1, e to the million is gigantic, 1 over a million is very, very close to 1, and it continues doing that. If the power is negative, what happens? The negative gets distributed to the numerator and denominator. So this means that nothing moves to the denominator, but that e should move to the numerator, and then you apply the power. So that's why we're going off to positive infinity in that direction. Okay. Now, exponential functions and the concept of e show up in simple interest, and are not in simple interest, but in compound interest and continuous compounding. All right, so with that in mind, let's take a look at the equation. So simple interest is just principal times the rate times the time. People are used to that. Future value of a something, future value of an account would be future value is A, P is principal, R is the rate, N is the number of compounding periods per year, and T is the number of years. That works for if you're going to compound, typically a bank account would compound monthly. What about if I did it daily or hourly? The more I compound, the better the future value gets. But if you squint and look really close, you can kind of see that 1 plus 1 over n to the n in there. That's what we're talking about. As n goes off to infinity, 1 over 1 plus n to the n goes off to e. So what we end up with is a limit of e, and then what we have is continuous compounding. So the continuous compounding is p e to the RT. Continuous compounding is not something you're typically going to see in a bank account. Continuous compounding is what you're going to see when you have a colony of bacteria, or you have a radioactive element that's undergoing radioactive decay. Those are the real world places where you're going to see continuous compounding. So that in mind, let's take a look at future values for $5,000 investment that pays 6.5% interest per year. And then how much money do we have after 10 years? So let's do it. So if I compound annually, let's just kind of run the point home here. Compounding annually means N is 1, quarterly, N is 4. Monthly, that's usually what bank accounts do, N is 12. Daily would be 365. And then compounding continuously is when we use the other, we use a different equation. So what do these look like? Future value is equal to the principal times the rate. The rate is 6.5%, but I can't do math with percents, right? So I have to convert the percent to a decimal. R over N raised to the 1 minus 1 plus 0.65 over 1 raised to the, oh, I'm doing the monthly Fabian equation. Try that again. Principal times 1 plus the rate raised to the nt. Yeah. There we go. That's hilarious. So that's the equation. So that means I'm looking at 5,000, 1 plus 0.065 divided by 1 raised to the 1 times 10. Plug that in your calculator. You'll get a number, then compound quarterly, monthly. All the numbers are done in the notes, in the completed notes that are posted in that lecture. So only thing that changes between these is n. Every other number stays exactly the same. 1 plus 0.065 divided by, if I'm compounding quarterly, now n is 4, t is 10. So those stay the same for compound monthly, compounded daily. Compounded continuously is where we use the compounding continuously formula. So for this problem, $5,000 times E raised to the rate 0.65 times time, which is 10. You'll find out that compounding going from annually to quarterly has a much larger difference than daily to continuous. But you can find those numbers in the notes. I'll come back and complete those as well. You'll find those in the notes. So this is just I want to show you where there's a real life situation. All right. Next, And this is kind of what we have been building towards. I have the dollar value V of t of a certain car model that is t years old is given by the following exponential function. V of t is equal to 25,900 times 0.88 raised to the t. This is an exponential equation or exponential function. And it's got a slightly different setup, right? We said that exponential functions had that f of x is equal to b to the x. Well, this one is f of x equal b to the x, but it has a constant out front. And that's fine, right? You can have a number in front that doesn't have a variable in it. It's just a non-zero constant number, and it just sits right there. And that's absolutely fine. So you can have your exponential function in this form. You could have a variable here. You could have a constant here. You could have a constant in front of the t. You can add and subtract on the outside. You can add and subtract on the inside. They're all exponential functions. But let's do what this says. Find the initial value of the car and the value after 11 years. Initial value means no time has passed. No time has passed means time is 0. So that means if I want the initial value, I use my exponential function, 0.88 raised to the 0. Anything to the 0 power is 1. So that's 25,900 times 1, which is 25,900. So the car's value is $25,900 to start. What is the value after 11 years? The value after 11 years is 25,900 times 0.88 raised to the 11th. And let's do it on Desmos because I have it. 25,900 times 0.88 raised to the 11 is $6,347.59. So as time passes, my car is losing value, and that's how it is for 90% of cars, right? My Honda Civic is not getting more expensive because it's hard to get or popular or any of those things that make car values go up, right? It's it's kind of a bland, it's literally bland gray, and it's not getting more expensive as time goes. If I bought a Corvette or a McLaren or a Ferrari, some of those cars do increase in value over time, but most don't. So after no time has passed, that means when I initially got the car, it was $25,900. After 11 years, now it's worth $6,347.59. So I've lost money. So this means I have exponential decay. How much am I losing? All right. What is my rate of loss? That's my rate of exponential decay. Okay. Well, we learned when we took our graphs and we inverted them, we learned that if my base is between 0 and 1, my graph looks totally different than if it's greater than 1. So in this problem, the base is 0.88. So my rate of loss is 1 minus whatever the base was. 1 minus 0.88 is 0.12, and then convert that to a fraction. Or sorry, decimal, convert it to a percent. So this is what 12% loss per year looks like. Right, it's worth 12% less at the end of the first year than it was when you bought it. At the end of the second year, it's worth 12% less than the 12% less than it was worth after the second. So it kind of piles on itself. This goes down quite a bit quicker than if it were just losing $2,000 in value a year, right, or $1,000 a year. It would not continue to plummet each time. So with that in mind, if I want to know my rate of decay or growth, it's just how far off is my base from the number 1. If I've got loss, my base is going to be between 0 and 1. If I have growth, like I do in this problem, my base is going to be greater than 1. All right, so City has a population of 320,000 people. Suppose that each year the population grows by 6.25%. What will the population be after 7 years? So I need two things. First thing I need is an exponential equation that predicts the population. And then I need to plug 7 in for time and find out what that future population will be. So if I grow at 6.25%, then that means that my base is 1 plus 6.25%. Now, I just told you can't do math with a percent, and that's still true. So I got to convert the percent to a decimal. And I have found B. Now, what is this doing? The 1, if you take your initial value and you multiply it by 1, you get back your initial value, right? If you take your initial value and you multiply it by 0.0625, you get how much growth you have. What is 6.25% of my initial population? So when my base, this is why when the base is greater than 1, we see that growth. So if that's B, A is my initial value. Well, the problem starts with 320,000 people. So my population exponential equation looks like 320,000 times 1.0625 raised to the t. Right? That is what is running the show. And so I got that. So what happens when I what happens when I plug in 11? If that's P at T, or not 11, 7. I plug in 7, so in 7 years, if I see 6.25% growth every year for 7 years, I'm estimating that my population will be 489,162. Now the number, when you punch this in the calculator, you're going to get 161.8. These are people, so I can't have a decimal or a partial of a person, so that's why I rounded to just naturally rounded. If it's the decimal is greater, the number to the right is greater than 5 or greater, round up. If not, stay where you are. So that's my expected population 7 years from there. All right. And I'm going to skip the rest of those. These are just more examples of doing the same stuff. There's your exponential equation. Find the initial value, find the value after 10 years. If you want to buy a house, here's the monthly payment equation. You can plug that in, plug in the numbers you have. You're going to borrow $250,000, and you're going to do a 30-year loan with an interest rate of 7.245, which was the interest rate when I wrote this problem a couple days ago. Then you're going to figure out how much does that cost you total. Then you're going to do the same thing for a 15-year loan for the same amount. If you take a shorter loan, you usually get a lower interest rate. And then figure out what's the difference between taking a 30-year loan and making minimum payments every year, taking a 15-year loan and making minimum payments. Last part of 3.2, the part I really want to get at is solving exponential equations. In these, you have the property that if I have a to the u is equal to a to the v, then u equals v. The base has to be the same. Okay, I know u and v look similar, and it drives me crazy that they get used all the time in math, but they do. They kind of get paired up like m and n. So a to the u is a to the v. So what this means is if I can write both sides of my equation in the same base, I can use the exponents to solve for my variable, because it's an exponential equation, which means the variable is in the exponent. So 3 to the x plus 5 is equal to 81. I don't know 81 in terms of 3, but I do know it in terms of 9. 81 is 9 squared, and I know 9 in terms of 3. 9 is 3 squared. So I have 9 squared, well, that's 3 squared squared. Raising power to a power means you multiply. And the property says if 3 to the x plus 5 is equal to 3 to the 4th, then x plus 5 equals 4. Solve for x, subtract 5 from both sides. And we're going to find x is equal to -1. And then we go back and check, because extraneous solutions are possible when we do these problems. So to check, I go back to the original, so that's 3 to the -1 plus 5 is equal to 81. -1 plus 5 is 4. 3 to the 4th is 81. That checks. So then my solution set contains -1. Okay. It's rinse and repeat for these. Next, I've got bases. They seem to be related. How? I'm not sure yet. So 5 to the x squared plus 8. Can I rewrite 125 in terms of 5s? Yes, I can. 125 is 5 cubed. And notice 125 got swapped out with 5 cubed, but I kept the relationship between 125, that's 125 raised to the 2x, and this is 5 to the 3rd, all raised to the 2x. They're the same thing. Raising a power to a power means multiply. So 5 cubed raised to the 2x is 5 to the 6x. And the rule says that I've got the same base, therefore the powers are equal. Now, this one's quadratic now, which means the process of solving is a little different. Everything needs to go to one side, and then we're going to determine if we can factor. So subtract 6x from both sides. X squared minus 6x plus 8 equals 0. Two numbers that multiply to positive 8 and add to -6. Okay, if they multiply to a positive but add to a negative, they're both negative. And the numbers are -4 and -2. Two things multiply to 0, meaning one of them is 0. X minus 4 equals 0 means x is 4. X minus 2 equals 0, which means x is 2. So we got to check them. So check 4 and check 2. And the way we check is to plug it in, or a way that I have learned to do it is to use your calculator, and I want you to just think about what checking does. All right, what does checking for do? I go back to the original, and I say, okay, that's 5 raised to the x squared plus 8. That's the left-hand side. And then the right-hand side is 125 raised to the 2x. And what I want to know is, when I plug in these numbers, do I get equality? So how do I figure that out? I just go in here and swap out the x for a 4. Okay. And it didn't. There we go. I was like, that's not good. I didn't indicate that was 2 times x before I typed it in, so the problem thought it was 125 to the 24th power. So are these equal? Yes, these are equal. So that means 4 checks. If I want to check, okay, how about 2? Then just replace that 4 with a 2, replace that 4 with a 2. You find equality, you've done it. All right, so checked with Desmos. Left-hand side goes into one line, right-hand side goes into the other. If you want, you could even name the left-hand side f of x and the right-hand side g of x, and then plug in the numbers to the notation. But checking that with Desmos gives you the answer. If you check this one by hand, you're not going to actually calculate, because look at the numbers that we that showed up. Right, this is 244 million. You're not going to actually calculate this number on the left, this number on the right, and then see if they match. If you're checking the problem, you'll just end up with 5 to some number equals 5 to some number. Are those numbers the same? And I think it's 5 to the 24th equals 5 to the 24th. All right, so next. Oh, and let me write this. Solutions. Solution set contains both 2 and 4. Next, I have an exponential equation. E to the negative x squared is equal to e to the x squared plus times 1 over e cubed. I got to clean this up first. So the only rule that I know at this point is powers. If I get the same base to powers, I can set the powers equal. So I have e to the negative x squared. I don't have all the factors on the right I don't have it all in one e. I have 2 of them here. So let's deal with power raised to a power. So this is e to the x all squared. So multiply e to the x, so x times 2 is 2x. And then times, this is 1 over e to the third. It's not doing me any good in the denominator. So I'm going to bring it up to the numerator, and I'm going to do that by changing the sign. So 1 over e cubed is e to the negative 3. Why is that helpful? Because now on the right-hand side, I have multiplication with the same base. So that means I add the powers. 2x plus negative 3 is 2x minus 3. I did an extra step there because multiplication always means plus, and then the fact that the 3 is negative is what makes this a minus. I don't want you to get confused and think that multiplication could lead to subtraction. It can't. So now I have the same base on both sides. So now I know that negative x squared is equal to 2x minus 3. It's a quadratic. Everything to one side. It's a lot easier to add Well, I'm going to add x squared to both sides so that my leading coefficient is positive, which makes factoring easy. Plus 2x minus 3. And then does this factor? Yeah, two numbers that multiply to -3 and add to positive 2. I'm going to write it again just the other way. 2x minus 3 equals 0. Multiply to a negative means one of these is plus, one of these is minus. And then which one's larger? The middle term, the b, the sign of the coefficient b is positive, which means the positive number has the larger magnitude. So this is plus 3 minus 1. By the zero product principle, two things multiply to 0 means one of them is 0. So x is -3 or x is 1. And then we check. Again, I would encourage you to use Desmos because you have to go back to the original problem, e to the -3 squared is equal to e to the -3 squared times 1 over e cubed. -3 squared is 9. There's a minus on the outside that gets to live. It hangs on. -3 times 2 is -6. 1 over e cubed is e to the -3. E to the -9th is equal to same base, add the powers. E to the -9th, they check. So that's what I meant by if you don't do this on Desmos, you won't actually end up with the result of the left-hand side, the right-hand side. You're going to end up with two parts that both have the same base and the same power. If I get the 1, that's e to the -1 squared is equal to e to the first squared times 1 over e cubed. 1 squared is 1, but the negative is outside, so that's e to the -1 is equal to e to the first squared is e squared. 1 over e cubed is e to the -3. And now I got the same base on the right. 2 plus -3 is -1. They check. So the solutions are -3 and +1. How do we feel about that? How are we doing? It's been very quiet today. All right, last one. Because it is just oodles of fun, and I already did some work here. Yeah, this content, and I still don't quite understand how, but the majority of this class, if you took Algebra 2 in high school, the majority of this class is review until we get to this last chapter. This last chapter feels like it just falls out of the sky. The power rules, the exponents, the fractional powers, all that stuff feels alien because if you did it, it wasn't very long, and now we're focusing on it. So, last problem here, I don't have, so every time before this, I've had one of the bases was the base I wanted to turn the other one into, right? Prior to this, I had bases on both sides. I wanted to end up with E. On this one, I had a 5 and a 125. I turned the 125 into a 5. Up here, I had 3 and 81. I turned the 81 into 3 to something. Now I have two bases that are not, neither one of them are the base I want, but they both have 3 in them, right? 1 over 9 is 1 over 3 squared. And 27 is 3 cubed. All right, 1 over 3 to the 1 over 3 squared is the same thing as 3 to the negative 2. And then 3 cubed raised to the x plus 3 is 3 times 3x plus 9, right? Power raised to a power means you multiply. On the left, I'll tell you what, let's actually do that. Do this both in one step. That's 3 raised to the 3 times x plus 3, and then distribute on both sides. Negative 2 times x, it's negative 2x. Negative 2 times negative 1 is positive 2. And then on the right, I have 3 to the 3x plus 9. And this was the goal. I have the same base on both sides. So now I know if these two are equal, then negative 2x plus 2 must equal 3x plus 9. All right, so solve. This is linear. It's not a quadratic, so I don't get everything on one side. Instead, I get everything with an x on one side. I'm going to move everything with an x to the right, which means everything without an x is going left. Negative 2x plus 2x is 0. 2 minus 9 is negative 7. 3x plus 2x is 5x. 9 minus 9 is 0. Get x totally by itself. And I find out that x is negative 7/5. Okay? To check this, okay, if you try to do this by hand, it takes more steps than the problem actually did. So I went ahead and did the same thing in Desmos. The top line is the original left-hand side, replaced by negative 7/5. The bottom, the second one is the original right-hand side with negative 7/5 plugged in for x. My answers come out identical, so the left-hand side and the right-hand side are equal, which means this checks, which means the solutions of the solution set contains negative 7/5. All right, so that is the bulk of 3.2, or that's all of 3.2. Any questions? Because I'm going to introduce you to logs very quickly. We don't have a lot of time, but I do want to, if I can talk about them really quick, I will take a couple minutes to do that. Any questions, any problems? No? All right. Then let me jump over. Yep, logarithms and exponents. That's the whole chapter. So the next set here is logarithms. Okay, so 3.3 covers logarithms. Base exponent equals answer. Let me think about that. I think I know what you mean. Yeah, they're inverse. Yes, they're inverse functions, right? So if I take the log of an exponential, I'll get back to what I started with. But let's deal with the log. What does it mean? Okay, so this graph is log base 2 of x. Okay, what does that mean? A logarithm is literally, I'm gonna stick a y in there just to make it easier to deal with. Log base 2 of x equals y means what power do I raise the base to in order to get the argument? All right. Now, argument is my term. That's from my computer science days. Argument for me is what's in parentheses here. So log base 2 of x means, if I'm taking log base 2 of x is equal to y, the answer to log base 2 of x is what power do I raise 2 to get x, right? So these do go back and forth between exponential and logarithmic notation. So that's 2 raised to the y equals x. Okay? Sometimes the best way to solve a logarithm is to rewrite it in exponential form and then just solve it. You get your exponential equation and then you can solve. So the graph I have is log base 2 of x. Using the rules of transformation, let's sketch the graph of log base 2 of x plus 4 minus 1. Same manipulation as before. This is a plus 4 inside. So that means go left 4 units. And then that -1, that -1 on the outside means down 1 unit. So any point you can find on here, 4 down, 4 left and 1 down. So 1, 0, 1, 2, 3, 4 goes to here. 2, 1, 2, 3, 4, and down. And then it looks like 4 and 2. 1, 2, 3, 4, and down. And then we get our graph. And that's the idea. All right, so transformations work the same. The same rules apply. If you mess with the inside, it affects x. If you mess with the outside, it affects y. All right, so I'll stop there. Check out the lectures for 3.2, 3.1, 3.2, 3.3, and 3.4. Instead of me just going over everything, what I'm going to do is I want you to watch the lectures, see if there's some confusion, look at the homework, see if there's questions. Yes, yeah. So check, see if there's questions from the lectures. Bring those to class on Thursday. And instead of me just reading everything or doing all the steps, we're going to focus on the parts that are causing trouble. All right? All right, y'all have a great day.